Okay, so let's do some examples using Bernoulli's law. Examples with Bernoulli's law, or Bernoulli's equation, I should say. So first, let's just think of a container that's filled with water that's not moving. So here's the container, here's the surface of the water, and let's say that the depth of the water is h. At the top, of course, the pressure, you call that pressure at point 1, is 1 atmosphere. This is water that is static, and so that's one limit of laminar flow. And so we can consider any other part of this to be 0.2 and legitimately use Bernoulli's equation. So what I'm going to ask is, what is the pressure at the bottom of the container, P2? So I'll remind you of Bernoulli's equation, P1 plus rho g y1 plus 1/2 rho v1 squared equals P2 plus rho g y2 plus 1/2 rho v2 squared. Now in our case, the fluid is not moving at the top and the bottom, so we can cancel those two parts out, and then we can solve for P2. So P2 is going to be equal to P1 plus rho g times y1 minus y2, where I've moved this part over to here and factored out the rho g. So that's pretty keen. So we can see that the pressure at the bottom of the tank is higher than the pressure at the top of the tank by an amount that's proportional to the height difference. So we could rewrite this as rho g times h. And so we know what the density of water is. That's 1,000 kilograms per meter cubed. And of course, we know the value of g. And so this is kind of interesting. It's showing you that the pressure at the bottom of the tank is just scaling linearly with the height of the tank. And so one thing that we might ask is, what is the required value of h for P2 to equal 2 atmospheres? So we can rearrange our equation to solve for h. So h would be P2 minus P1 divided by rho g. And so that's 2 atmospheres minus 1 atmosphere divided by 1,000 kilograms per meter cubed times 9.8 meters per second squared. By the way, when you are writing up homework problems, if you like writing a step like this as part of your work, if that helps you to plug in numbers correctly, you're welcome to do it, but you don't have to. As long as you have defined all of the symbols here, you can just plug it in. So if we plug this in and convert the height to feet, this turns out to be 34 feet. So that's telling you for each 34 feet of depth of water you go down, the pressure increases by an entire atmosphere. And obviously that's something that's quite important if you are going diving, deep sea diving, scuba diving.